Welcome to this evening session. And this session is about processing for digital health records. During the session, we will have three speakers, Davide Chicco, Georgios Peikos, and Giancarlo Milanese. So let's start with the first speaker, Davide Chicco. Davide is a researcher at the Department of Informatics, System and Communication at the University of Milano Bicocca, working in a Tails laboratory. Today he will present us his works named Longitudinal Clustering Applied to Multi-Visit Data of Patients with Psychological Health Issues. Davide, I leave the floor to you.
Thank you. Thank you, Alessandro. Thanks for being here, everybody. My name is Davide Chicco. I am an assistant professor at the University of Milano Bicocca. I'm going to present today a work on longitudinal clustering applied to data of patients with psychological health issues, a project that we are carrying out with Francesca Gasparini and several collaborators at Consiglio Nazionale delle Ricerche. In particular, this is the main work by Patrizia Ribino, which is our collaborator, and she did most of the job, most of the work, so we are very happy to work with her. I will first say something about dementia. I will introduce the OASIS 3 dataset that we used. I will say something about how to perform clustering on dementia data, and I will briefly report the longitudinal clustering algorithm that we use, that is k-means, with the soft DTW distance for trajectories of patients. We'll show some evaluation results and results on the relevant features of this clustering, and then mention some future developments. So we all know that dementia is a big problem worldwide. We have more than 55 million people that suffer from this disease, and most of them live in low and middle income countries. And also this can result from a variety of diseases that affect the brain, where Alzheimer's disease is the most common form of dementia that occurs in 60 to 70% of cases. And it's also the seventh leading cause of death worldwide, and one of the main causes of disability. And also handling patients with dementia and Alzheimer's disease is a huge problem, because it's extremely expensive, and there are a lot of informal carers, like family members, close friends, that take care of these people. And women are also disproportionately affected by dementia, both directly and indirectly, because they have more likely to get dementia, and they also provide the 70% of care hours of people living with dementia worldwide. So the data of electronic health records can be useful for computational analysis, because they can provide information about the trends of these diseases, and differently from other diseases like breast cancer or other stuff, we cannot use a single visit data set, because it doesn't say that much about the trend of the patient. So we need to use data sets that have multi-visits, multiple assessments, multiple data, and which unfortunately are not available, not very available. So one of the few data sets that is publicly available, it is well curated, is OASIS 3 dataset, which means Open Access Series of Imaging Studies 3, and was collected at Washington University in the United States, and provides data of magnetic resonance of images, and also clinical data of approximately 1,000 patients with approximately 600 cognitively normal adults and 500 individuals at various stages of cognitive decline from 42 to 95 years old. And these data sets are uniform, and is coordinated by this center, UDS, that merge together different data sets of different types. So we don't have only the images, but we also have clinical features about these patients at multiple visits. And that's what we did. That's what we used. And in this data set, they assess the dementia through the CDR scale, clinical dementia rating, and also the clinical dementia rating scale sum of boxes, and the mini mental state examination MMSE that we are used commonly in several studies. All the patients were required to have CDR lower or equal to 1 the baseline visits, meaning almost no dementia. And the neuropsychiatric inventory NPI was used to assess neuropsychiatric symptoms NPS with interviews that would ask questions about 12 domains, delusions, hallucination, agitation, aggression, depression, apathy, and so on. And then this was resulted in a score from 0 to 3 corresponding to the severity. The behavioral assessment was done through the geriatric depression scale, GDS. In the end, we had this data set diagnosis for of 3 kinds, so cognitive normal, CN, with dementia, or with uncertain diagnosis. And we take care of these labels in our clustering. And we decided to use only data of patients that have at least with 5 consecutive visits on annual frequency, so with a tolerance of 2 months, so that we could have a more consistent cohort. And in the end, we had 166 subjects with these conditions. In general, it's you know that we can use supervised or unsupervised methods. Medicine is mainly unsupervised, meaning that we don't know the labels of the patients until the very end. So it's more realistic to apply unsupervised methods. In this case, it's not a static data set, as we said, so it's a multi-visit one, and we needed to apply a clustering to the trajectories of patients. We decided to use k-means, longitudinal k-means, which is one of the simplest methods, because this was the first step of our project. And our collaborator, Patrizia Ribino, decided to avoid using the Euclidean distance that we use usually in this method, but she proposed to use this soft dynamic time warping DTW distance for clustering, so that we could find significant groups of patients that could maybe have a common trend in the future. DTW used the barycenter, not the centroid, and is defined as a time series that minimizes the aggregate distance between itself and the other time series within a given subject. More specifically, dynamic time warping is an algorithm for measuring the similarity between 2 temporal sequences, but these temporal sequences can also have a different speed, and so it considers the distance between the 2 sequences by warping the time axis by merging it or scratching it, and it's called soft because it has a probabilistic function that handles the constraints of its formula, and that's why it's different from the hard, the DTW that is used commonly. And so that's an example taken from Wikipedia with the dynamic time warping between 2 piecewise linear functions. The time warp relation is represented by the dotted lines, while even if the two series have a different speed, have a different trend. So we applied this method to this system to k-means with the typical k-means steps, initialization with a number of clusters, the first assignment that where the data of the nearest centroid is assigned. And you use there the soft DW distance, then the update step, and the conversion check to see if we needed to do another step for k-means, and then the output that is the final cluster, so in our case, the clusters of the trajectories of patients. We applied the typical clustering evaluation metrics that are used, so the silhouette score, the Kalinski-Albatz index, and the Davis-Baldwin index, where the silhouette score needs to be maximized, the Kalinski-Albatz index needs to be maximized as well, and the Davis-Baldwin index needs to be minimized. And we found out, as you can see, that the best number of clusters were 2 or 3, and we decided to apply this number of clusters and see if the clusters found had a medical meaning, as some related to the features. So with two clusters, we noticed some different in trends. For example, for the feature IRR, which is irritability, that clearly was defined, separated between the patients without irritability and the patients with mild irritability. It's similarly to what happened for agitation, and while for the other features here, like anxiety or dysphoria or apathy, there were not so many differences, so the trends were somehow similar. And we then also checked the results of our clustering techniques, or longitudinal clustering with two clusters, compared to the labels of CDR and the CDR-SB and the mini-mental state examination that we excluded at the beginning. And we noticed that for the mini-mental state examination, the two clusters were quite similar, as you can see in the third plot. But for the CDR clinical dementia rating, we clearly saw that the cluster number 1, that is the blue bars, are all clusters of values around 2, between 2 and 3, which means moderate dementia. And the other cluster, that is the cluster 2, the orange cluster, got all values between around 0, so a little more than 0. That means no dementia. So it's relevant to notice that our clustering application without ground truth, without the labels, was able to discriminate these two groups in such a clear way, at least for the CDR, not for the mini-mental state examination. We also tried with 3 clusters that were somehow split this way, with the first and the second cluster were somehow confirmed, and there was a cluster of patients in the middle of element share between the two clusters of the two cases. And also in this case, there were some features that were more discriminative than others, which is basically what you can see on the right, with irritability that had 2 clusters going on the same trend and other clusters staying up to 0. Then there was the 3 clusters for agitations, where basically sharing a common trend, the orange and the green one at the beginning, but in the end the orange would merge with the blue one, and the green would still increase. For anxiety, the 3 clusters were starting somehow at the same level, and then they arrived to 2 different trends, with the third cluster going up, meaning more anxiety. There were no significant difference for dysphoria. For a geriatric depression scale, we see the 2 clusters, the green and the orange one, were together, and the blue was lower. And also for disinhibition, there were not much differences. Again, we tried to see what were the values of CDR, CDR-SB, and MMSE for this case. And we noticed that also in this case the results were quite promising, because we had that the green cluster resulted having the highest CDR, meaning higher dementia, higher impairment, while the blue cluster stayed around 0, so it meant no dementia and good status among all the visits, while the orange one was somehow in the middle. So, while for the minimal state examination, the results were more stable across the 3 clusters, even if with some little difference. The results we noticed on these features were interesting, so we saw that we were able to deduce that as is explained in the scientific literature, even if Alzheimer's is a cognitive disorder, it's also linked to the development of neuropsychiatric symptoms, as probably many of you that work in medicine already know. And the trend of Alzheimer's can affect these features that we just mentioned, such as anxiety, dysphoria, changeability of mood, euphoria, impulse discontrol, and other ones, such as agitation, irritability, disinhibition. And in the individuals with Alzheimer's disease, there are moderately increased values for dysphoria and disinhibition, and more evident increment for irritability, apathy, agitation, and anxiety. And these 2 last symptoms would get worse significantly during the last visit, so the trend was worsening. And we assessed, we noticed that similar to what we read in the literature, the new onset persistent personality and behavior that change after 50 years old, rather than signaling a new onset of psychiatric disorder, can be an early manifestation of neurodegenerative disease, and that can affect these patients more deeply and more commonly than simple changes of personality due to the mood or to the word. So that's something to keep in mind. And so to conclude our study, we were satisfied about the results because our approach, especially with the 3 clusters, was also able to differentiate groups of patients that would get worse from the dementia side, but also that would get some risk factors that would lead the patients to dementia. And so these clusters can be useful in the future, maybe for a medical doctor to state what is going to be the trend of a particular patient based on these clusters. And we also had some limitations, and unfortunately all the tests were done on a single data set, so we have a lack of generalizability, but that's the first step of our project. So we can reapply the same method to other data sets. We recently published an article in a scientific journal by data mining, so that is called the Multivariate Longitudinal Clustering Reveals Neuropsychological Factors of Dementia Predictors in Alzheimer's Disease Progression Study. So you can read more about this project by reading this paper that we just published, and was a teamwork, but especially Patrizia Ribino did most of the job, so we're very happy to have her. And that's it for the moment. Thank you.
Thank you, Davide. Let me introduce you the next speaker of this session. That is Georgios Peikos Ioannis, that is a postdoc research fellow working in the Information and Knowledge Representation, Retrieval and Reasoning Laboratory at the Department of Informatics, System and Communication of the University of Milan Bicocca. Today, he will present us his work named LLM-based information extraction from clinical notes for downstream healthcare applications. Georgios, I leave the floor to you.
Great, thank you. Thank you very much, everybody. So eventually we will end up talking about LLMs, but before that I will give a broad spectrum of several NLP approaches that can be used, and I would highlight what are the pros and cons of each approach in order to extract information from clinical notes. And I will showcase some experiments that we have conducted in a specific healthcare application. The results I'm presenting is a summary of several works we have been working on the last few years. The first part of my talk will be about bringing everybody in the same page. So we'll present some context of what are clinical texts and why we need NLP approaches in this context. And I will showcase which approaches we can use and why, when to use each one of them. And the second part will be a specific healthcare application. So let's start with the examples. Clinical text can be provided in a semi-structured way, and these can be represented by diagnostic reports or lab reports as they're representing here. We can have some tables where we have semi-structured information with some values and units. Or we can have at the same document some unstructured information, which is usually the comments or observations from the doctor or other clinicians. Of course, there are many cases in electronic health records where clinical texts are completely unstructured, like admission notes, progress notes, etc., like the one synthetic case I'm presenting here, where it's a psychotherapy progress report note, let's say, where a psychotherapist may write some information about the session they had. Here, it might be the case that we have some highlighted sections, for example, results, and then following with the results or outcomes, but these are only for human readability. So in order for the clinicians to be able to understand and find the information, but not explicitly designed for systems or NLP systems. And this is why, because these clinical texts have the primary uses. Oh, it seems to be a problem with emojis. Okay, but in any case, because the primary use is to facilitate patient care, help people become better, and communicate information within a medical organization. But besides these, there are also the secondary uses of these clinical texts. We can use it in order to do research, to understand patterns, or even find patients to participate in clinical trials, and of course, administration staff, etc. In the talk, I'm presenting how we can use NLP approaches to automate these uses, mainly the secondary ones, in a cost-effective and time-efficient manner. First of all, why do we need NLP? We need NLP because these clinical notes are written for other purposes, to help people, not really for the secondary usages. This is, let's say, a bonus we have. Because of that, there are many linguistic challenges. There are abbreviations. There are relationship with ontology codes, for example, or negations. There is a lot of temporal reasoning we should to do. So in order to facilitate the secondary usages, it's not always mandatory to actually extract all this information. We need to be very specific on what we extract, otherwise we will not be able to have good performance on the secondary use we want. Besides these linguistic challenges, as I said before, clinical notes tend to be short, contain a lot of abbreviations, misspellings, and there are personalized writing in the end, because every clinician, even working in the same laboratory, in the same group, might have their own specialized way of writing. They might use abbreviations, they might not use abbreviations, etc. So for all these reasons, we need specific NLP tools in order to be able to handle these peculiarities. Over the years, there are many approaches. We start with standard rule-based approaches, move to machine learning approaches, and of course, nowadays, large language models. Now, I decided for this presentation to give the pros and cons of each of these approaches, because all of them have some pros. Let's start with a rule-based approach. Just to clarify for everybody, a rule-based approach can be as simple as a Python code that says extract every text that comes after the word results, for example. It's that simple. Here I have some example of these tools. They have some strengths. The most important one is that if you have a well-defined context, so if you want to design an NLP system to extract information coming from the same laboratory where they work the same clinicians, then rule-based approaches might be able to give you high precision. So, because the system is so well defined that there is no variability in the language used, and there is no the context is very well structured. And more importantly, because you design this rule-based in collaboration with the clinicians that actually will use the system. The problem is when you try to generalize these rule-based systems to, let's say, another department, or even when a new clinician comes in, then you might have problems with these rule-based approaches. Machine learning approaches, I will not stay a lot here because it can be summarized into term frequency representations of text and standard random forest for doing, which is something that in NLP have been completely replaced by transformers. In any case, I would like to highlight here that now we are not manually programming. We use data in order to be able to find patterns in our clinical notes and extract the information we want. So we can handle variations in phrasing or other things. But we start having the need for feature engineering, and especially we need to have data annotated so we can train these models to find the patterns we want. And this is the important thing to highlight, that we start moving from rule-based approaches to data-driven approaches. This became more evident with deep learning approaches like transformer architectures, let's say clinical BERT or bio-BERT, where we have embedding representation of words. Here, okay, before large language models, these approaches were the state of the art. They were having good performance in many clinical tasks. Here we don't need to feature engineering, and we are able to capture better the context and the semantics of texts. However, now we need larger labeled data sets, which for a medical organization is more expensive because having expert clinicians to actually annotate data takes a lot of time, and their time is not very cheap, let's say. And of course, as we move on from rule-based approaches to now deep learning approaches, we start moving from a white box to a more black box. So we are not able to understand why this information is extracted, why other pieces of information is not extracted, etc. So we are start to having stronger, flexible models, but they are now more hungry for data, and we are losing in terms of interpretability. And now we have large language models nowadays, with examples like ChatGPT or Gatordron, and more specific, trained on clinical and medical applications models. Here, we don't need, we can adapt these models after they have been trained with a very few data, which is what we call few shot, or even without the annotated data. And these models can generalize to many tasks that may appear within one organization. To give an example, when we are talking about a transformer like a bio-BERT, it might have a version of it that can extract drugs, mentions from text, but it cannot extract family history or past medical history of a patient. With LLMs, very simple, as I will show you later, we will be able to extract with a single model all this information. And this is a benefit we have with large language models. It might be the case that we have the illusion, and I use this word on purpose, that this large language model is the solution to everything, and this is not true, because a large language model, there are studies that support that they cannot identify negation in text, or they still struggle with abbreviations. I don't even comment on trying to understand the ontologies mentioned in the text, and they still have problems. The most important ones are, of course, the expense we have to do to train it. Usually this is done by private companies. We will be happy if we have access to open source models, but this is not always the case. We have a complete black box behavior. We don't even have access to how these models are trained. We don't know what kind of biases these models have. And in any case, we don't know what are the consequences of implementing these models in our systems. And in order for a medical organization, or in general, to actually create the infrastructure to support at scale the implementation of large language models is a significant investment. And what is called hallucination is, in practice, errors that these models can do. So these models, we have one. It might be applied to many tasks. It's flexible, it's fluent, but they are not always right. And we should know it. Lastly, an important observation is regarding the privacy, because especially in Europe, it's not so simple to just use an API to send patient information. It's more or less forbidden. Okay, so I gave you an overview of the different NLP approaches. Now I will summarize the findings of several studies we conducted where we applied these NLP approaches in order to tackle the task of clinical trials enrollment. So this is a very important task. How is it formulated? We have patient information coming from clinical notes or electronic health records, and our goal is to leverage this information in order to find clinical trials in which the patient can participate. A clinical trial is another experiment conducted in order to identify medical equipment or new medical drugs, etc. Why it is important to solve this problem? Because there is a significant delay on finding patients participating in clinical trials, and occasionally they even cancel them. The process of manually searching clinical trials for a patient is not very efficient currently. It's time-consuming, it costs a lot of money, and it's prone to human errors. What will be a solution? A solution will be to have a better system, a retrieval system, in which we give the necessary patient information, and this system can give us back clinical trials in which the patient can participate. In order to do that, the first step, and an important one, is to extract this information from the free text patient records and aiming to improve this process. In the figure, I present here how such a system will work, and now step by step I will try to explain it. So, we have a medical expert sitting like me in front of a computer. The first step is to select the patient for which she wants to find eligible clinical trials. This information is usually stored privately within the organization. So the system needs to fetch this data from the private database and pass it through a locally running NLP system. This system needs to perform the information extraction. As I said before, not every information that is presented within the electronic health record is essential for the task of finding clinical trials. So we need to use the system that can do it in a very good way. Just to clarify here, especially for the next part, okay, let's highlight this first, that we need to have expert user oversight because we are talking about medical applications, and in our opinion, it's very important that there is a synergy between systems and people. So the user needs to review the generated keywords, remove or add some of them. These keywords are used as a query in a search system, in a search engine, in order to retrieve clinical trials. I will give an example just to make sure that everybody understands. We all use Google to search, okay? And we go there and we write some keywords and we get as a result clinical trials. The system I'm describing here, the NLP takes a text and generates the keywords for us, used in a system, let's say, like Google, but it's much, much, much simpler. And instead of web pages, now we have clinical trials, the expert user. So this is how the system should work. And then finally, the expert user now needs to read the top-ranked clinical trials, and hopefully the user will be presented with those that the patient can participate, and the task will be finished fast. The NLP-based system, the information extraction one, can leverage many approaches that I presented before, rule-based approaches or large language models. Again, just to clarify, when we are talking about large language models, we do not do like pure programming. We access these models through text, what is called prompt. Here I'm giving an example of prompt, where we actually put a sample clinical note as entry, and we ask the model to identify medical conditions, treatments, and other information from the clinical note. So based on this information, the LLM here is instructed to generate the query that then will be used to retrieve the clinical trials. Okay, so now I'm passing to the benchmarking. So how did we identify which NLP system is doing this job well? We use benchmark collections, in which the documents we used are publicly available clinical trials from clinicaltrials.gov, which is a public database. For queries that simulate patient admission notes, we use a number of them. In the original publication, we used several data sets. Here I'm presenting one in which we use 75 patients. Now, in order to be able to understand which clinical trial is eligible for each for each patient, we asked experts to annotate for each patient, for each query, those documents, those clinical trials in which the patient can participate, so they are eligible. So we have our ground truth, and we can get some evaluation measures to measure the effectiveness of the systems. Now, the first performance analysis we conducted was aiming to identify which NLP approaches of those I presented before results to improvement in enrollment by retrieving more eligible clinical trials. We evaluated deep learning in combination with rule-based approaches, closed-source LLMs, and open-source LLMs. We use precision-10 as the evaluation measure, which measures the number of eligible clinical trials in the top 10 retrieved ones. And here I present to you the results. So in black, you can see the baseline. So here we do nothing. We use the original clinical note as it was given to us. In orange, you can see the performance achieved by the standard deep learning and rule-based approaches, so before LLMs. Then in blue, you can see several LLMs that were used with prompts in order to extract information and do the queries. Some things to highlight here is, first of all, standard transformer-based approaches in combination with rule-based approaches outperform on par with some LLMs. So LLMs is not always the solution to everything. Second is the fact that GPT 3.5 was performing better than GPT-4. So it's a newer, better version than GPT-4, but it's not performing well, and this is consistent also in other experiments. And finally, the top performance in this task, in this benchmark collection, was coming from an open source model, which was 7 billion, so a relatively small model that literally can run in one GPU. Okay, the second performance evaluation we wanted to do is what happens when we compare the performance achieved by large language models with that performance achieved by experts. So here we compare the effectiveness in retrieving eligible clinical trials using queries that have been created by medical experts with that achieved by the queries generated by LLMs. Again, we use precision-10, just a measure of evaluation, but the performances I will present, they are coming from a different benchmark collection. That will be the difference in the numbers. Again, in black is the performance achieved by doing nothing. Then, in orange, we see the performance achieved when we use the queries, the keywords created by expert users, and in blue, the performance by LLMs. We see that there are LLMs that can outperform the performance of experts. This does not mean, of course, that we can replace these experts by any means, because for other experts, A and D, we see that the LLMs cannot reach the performance. In fact, expert B and expert C tend to use long queries, many keywords, using information that is present inside the clinical node, while expert A and expert D tend to use short queries and leverage information that is not presented in the original clinical node, but by their own knowledge. So that's highlight the fact that we cannot replace experts, and that's clear. So, again, here we see that open source LLMs perform better than closed source LLMs, so there is no need to use GPT or OpenAI models in every application. We can try something which is open source and it's easier for us. So, the concluding insight. Expert-generated queries still lead, but there is strong performance from LLMs as well, and this suggests that LLMs and humans should work together in this task. In practice, if an LLM can process a vast clinical trial, extract some keywords that are close to those extracted by experts, that will reduce a lot the time that an expert needs to actually read and write these keywords. So there is a synergy here that can be helpful. Open source models perform on par or better than closed source models. Larger or newer models that are usually more expensive to use do not guarantee better performance. Fine-tuned transformer-based model, which is something that people do not use anymore, and they directly apply LLMs and closed source most often. Should be seen and should be still used as a baseline. And something that I didn't highlight is the fact that when you're performing this kind of task that you expect the LLM to follow your instruction, you should be using instruction-tuned models because there is a great difference between using the same model that doesn't know how to follow orders and the model that knows how to do it. So here is the three different papers that I used in order to create this presentation. There are more experiments and more analysis in all of them. And that will be all. Thank you very much.
Thank you, Georgios, for your presentation. Let's pass to the last speaker of this session, that is Giancarlo Milanese. Giancarlo is a postdoc research fellow working in the Information and Knowledge Representation Retrieval and Reasoning Laboratory at the Department of Informatics, System and Communication of the University of Milano Bicocca. Today he will present us his works named Integrating LLM and Knowledge Graph for Factor-Driven Health Information Retrieval.
Great, thank you. Good afternoon. I hope you can hear me fine.
Wait.
Yes.
Okay, okay, you can start. Thank you.
Okay, thank you very much. Good afternoon, and sorry for not being there. So today I would like to talk about this work that I did together with Giorgio Pecos, Gabriella Pasi, and Marco Viviani at the University of Milano Bicocca. And this work is related to a challenge which has become increasingly urgent in recent years, and which is the widespread presence of misinformation online. And misinformation is a general concern across several domains, but it becomes especially critical in domains like the health domain, where misinformation can have some critical and serious consequences for people's decisions and well-being. And mental health, in particular, is one area where there's been a noticeable increase in the spread of misinformation, as showed, for instance, by a recent analysis that showed the prevalence of inaccurate information among the top videos on mental health on TikTok. And also, besides social media, also large language models like ChatGPT have added another layer of complexity to this issue, because these models can generate information which sounds plausible and very convincing, but often this information is incorrect or misleading. And this is a phenomenon commonly referred to as hallucination. And also, Giorgio Pecos before me has highlighted a lot of limitations of large language models and issues related to these models. And so this is just a motivation to say that there is a need for systems that help users access trustworthy and accurate information online. And so our work is situated in the area of information retrieval, or IR, which is the task of retrieving resources which are relevant to an information need. So an example would be search engines, where a user with some information need expresses this need as a query, and then the IR system is supposed to return a ranked list of documents that are relevant to that query. And so traditionally in information retrieval, or typically often, relevance in information retrieval has been understood as topicality, so whether a document is contextually similar to the user's query. But in some domains, like the health domain, topicality might not be enough in some cases, because a document could be perfectly on topic, for instance, about anxiety, but still contain several incorrect or misleading claims. And so that's why in recent years, there's been a lot of work on developing systems that are able to score documents alongside other dimensions besides topicality, so including credibility, correctness, reliability, trustworthiness, and so on. And especially many systems have been developed in the context of the track, health misinformation track, which is a challenge that evaluates IR systems according to their ability to retrieve relevant, credible, and correct information. So a lot of progress has been done in this area, but there are still some issues because many systems developed in this context, in the health information retrieval context, and in particular, the state-of-the-art system, the one that achieved the best performance across the latest on the latest track health misinformation benchmark. So these models heavily rely on large language models for several tasks, including answer prediction, so directly predicting the answer of a user query, or judging the correctness of a document. And as we already said, so these LLMs are very powerful, but they are unfortunately prone to hallucinations and to generating incorrect or misleading information. And in domains like health, this raises serious concerns about the risks associated with using such models for judging the correctness of documents. And so in our work, we take a different approach. So we recognize that LLMs are very powerful tools, so we still rely on them. But instead of using LLMs to directly judge the correctness of a document or to answer user query, we simply use them for a very focused task, which is to identify and extract factual claims from documents and structure these claims in the format of an RDF triple, so that later in the pipeline we can verify the correctness of documents by comparing these triples to an external source of reliable and trustworthy information, which in our case is a knowledge graph. And so we still use the strengths of LLMs in extracting and structuring information, but we avoid using them directly for truth judgments. So in the rest of the talk, I would like to present this system. Starting from the offline phase, which are all of the steps that are necessary to implement before any query is processed, like the construction of the knowledge graph, then moving on to the online phase, so how our system processes queries, and finally some experiments and discussion. And so, as I quickly mentioned, the very first offline step is the construction of this health knowledge graph. And so the idea in this case is to build a structured representation of knowledge that we can use later to verify the correctness of claims extracted from documents. So to do this, we start from Wikipedia, which is a large-scale knowledge graph derived from Wikipedia, and we run Sparkle queries focused on extracting medically relevant entities and relationships like diseases, drugs, medications, treatments, symptoms, and so on. And so at this point, the output of this extraction process is a knowledge graph which contains some statements in the form of triples, in the RDF format of subject, predicate, and object, like for instance, anxiety disorder is a disease with medication anxiolytic and treatment psychotherapy. And we can also visualize all of these collection of triples as a graph. So now that we have this knowledge graph, which should be a source of reliable information, we proceed to extract claims from the documents that we want to retrieve through our information retrieval system. And in this case, we use an LLM to identify statements in documents that express some factual claim and to structure these claims as an RDF triple. And in this case, this triple is associated with a truth value, either true or false. So just as a couple of examples, for instance, if we have a web page that asserts that some relation holds, like anxiety can be treated by psychotherapy, then the LLM is expected to extract the triple anxiety treatment psychotherapy associated with the true truth value. And this will be a positive triple. And instead, if a document asserts that some relation doesn't hold, it isn't true, like drinking tea is not effective in treating anxiety, then the LLM is expected to extract the triple anxiety treatment tea, but now associated with a false truth value, because according to the web page, that triple is false. And so now we have our knowledge graph and our triples from documents, so we should be able to verify the correctness of the triples by comparing them with the knowledge graph. However, we know that knowledge graphs are often usually incomplete, and so our knowledge graph that we extracted from Wikipedia might not contain enough medical information to be able to verify the triples that we extracted from the whole collection of web pages. And so in order to try to improve the coverage of our knowledge graph, we implement an additional step. So we use a similar process by using an LLM to expand our knowledge graph. And in this case, we don't ask the LLM to extract triples from any web page, but we start from reliable sources of information like Wikipedia abstracts, which are short descriptions of the entities of Wikipedia. And so the source of this extraction should be reliable. And for instance, if we have this Wikipedia abstract about anxiety listing several symptoms of anxiety, then the LLM is expected to extract all of these triples like anxiety symptom, restlessness, irritability, and chest pain. And because the source is reliable, also these generated triples should be still, which will maintain a good quality of in the overall knowledge graph. However, because we know that LLMs are not perfect, but rather prone to errors, we have also implemented several safeguards to try to mitigate the possibility of generating hallucinations. And so, for instance, it might happen that an LLM extracts a triple that contains terms that are not actually present in the original Wikipedia abstract. And so, because this is evidence of hallucination, we filter out these triples. And another example is contradictory triples. So across all of the Wikipedia abstracts, it might happen that an LLM generates the same triple once associated with a true truth value and once associated with a false truth value. And this happened in very few occurrences, only 0.03% of all the generated triples were contradictory. But also in this case, we simply filter out these contradictory triples. And so through these filters, even if you're using an LLM, we try to ensure that the expanded knowledge graph remains clean and consistent and as reliable as possible. And so now that we have our source of reliable knowledge in the form of a knowledge graph and all of the triples extracted from the documents, we can finally verify the correctness of these triples. And we do so by assigning one of 4 categories to each triple. For instance, if we have a web page D, a document D, and from this web page we have extracted the triple TSPO, so this according to this document, SPO is true. If we can actually verify that SPO is true by checking that it is inside our knowledge graph, then that triple is a true positive. And instead, if we cannot find that triple inside our knowledge graph, this means that the web page asserts something which isn't supported in our knowledge graph, and so it's a false positive. And instead, let's say that we have a negative triple extracted from the document D, so triple F SPO. SPO is false according to the document. And if instead we find this triple inside our knowledge graph, then we know that that triple is a false negative. And on the other hand, if indeed that triple isn't present in our knowledge graph, so the web page is denying something which also doesn't appear in our knowledge graph, then that becomes a true negative. And once we have all of these categories associated with each of the triples for each of the web pages, we can compute an overall correctness score for each document, depending on the number of true positives, true negatives, and false positive. And we do so with that simple formula that you see in the top left corner. And so we have 2 terms. The first term, the number of true positives over the number of true positives and false negatives, simply reflects how often the document is correctly asserting true facts, while the other term, so true negatives over true negatives plus false positive, is simply reflects how often the document correctly rejects false claims. And just to see a simple example, let's suppose that we have these few triples in our knowledge graph related to treatments of anxiety. So according to our knowledge graph, anxiety could be treated by medication, psychotherapy, and D. Which is just an example, so I don't know if this is accurate information, but let's suppose that our knowledge graph contains this information. And let's also suppose that we have a web page which tells that anxiety can be treated by psychotherapy and medication, but not by drinking tea. So, according to our knowledge graph, the first two triples extracted from this web page will be true positives, while the last triple, which asserts that anxiety cannot be treated by tea, will be a false negative. So that overall the correctness score will be 0.66. So that once we have all of these correctness scores for each of our web page, essentially all of the complicated steps are done, because the final offline step is a standard one in information retrieval, which is just the indexing of the whole collection, and which will enable the efficient retrieval of the indexed documents as soon as a query arrives, so that we can move to the online phase and see that, for instance, if a query arrives asking for treatment of anxiety, whether T is a treatment for anxiety, our information retrieval system, through the index, will immediately be able to provide topically relevant documents that should satisfy this, should answer this user query. And so far, in this initial step, we only consider topicality, so we don't consider yet the correctness score. We measure topicality by using a standard BM25 algorithm, which is often used as a baseline in information retrieval systems. So once we have this initial ranking of documents only according to topicality, the next step is integrating the correctness scores. And so continuing from the previous example regarding treatments to anxiety, let's say that so we have, again, those triples: anxiety treatment, medication, psychotherapy, and T. We have this initial ranking. We can retrieve the pre-computed correctness score for the documents. And for instance, we see that the first two documents have a correctness score of only 0.5 and 0.66 due to the fact that they contain a false negative among their claims. And so if we simply do a linear combination of the topicality and the correctness score, we can push the correct documents among the top results in the ranking, and instead decrease the position of the of results that are topically relevant but possibly not correct. And this is a very simple example, because in practice we would have thousands of documents. I mean, a collection of millions or billions of documents, and thousands of documents in the initial ranking. And also the documents will be much more complex, and so on. But this is just the idea of how the system works. And so we can move on to see how it performs. And we have evaluated the system on the track health misinformation collections from 2020 until 2022. And these include around 1 billion English web pages and 150 queries related to health, and also including mental health. And we adopted this evaluation metric called compatibility, which measures the similarity between the ranking provided by our system to an ideal ranking. And this evaluation metric considers both correctness and topicality. And these are the results that we obtained on the three collections. In particular, we evaluate, so we compare our system when it provides the initial ranking of only topically relevant document against our system when it also integrates the correctness scores. And we evaluate three versions of the compatibility score. In particular, compatibility with helpful documents, which would be the documents that are both topically relevant and also correct. So we want the score to be as high as possible. Also, compatibility with harmful documents, which would be the documents that are possibly topically relevant but incorrect. So we want this compatibility score to be as low as possible, and also the difference between these two scores, which essentially evaluate how well our system promotes helpful documents over harmful documents. And so we see that in general, we get improvements across all data sets and scores and evaluation metrics, but so we get some positive results. The results are not particularly strong. And this is due to several reasons and factors, both linked to the quality of the data sets, but also linked to some limitation of our system, of course. Because what we have evaluated is a very simple version of our system. It's almost a proof of concept. And so seeing already some positive results is promising in this sense, but the performance is still below the one from the state-of-the-art system, which instead employs an LLM to directly answer queries and judge documents. So an advantage that we have at least is that our system should be more trustworthy and explainable due to our reliance on a knowledge graph. But still, as I said, there are several limitations. One of them is our adoption of the Wikipedia knowledge graph, which is a very convenient graph to use, but it's not the most complete and reliable one. And so it may still happen, despite also our best efforts to expand this knowledge graph by extracting triples from the Wikipedia abstracts, it may be possible that some claims, some true claims present in the web pages are judged as false because of absence of information in our knowledge graph. And another limitation is tied to the way that we compute correctness at the document level, because when we compute the correctness of a document, we consider all of the triples that appear in this document. But for instance, a document will contain many true triples about depression and very few false triples about anxiety. So the overall correctness of the document will be still very high. But for a query regarding anxiety, this document will not be helpful, because regarding anxiety, it only contains false statements. And so we have already experimented with a variation of our formula to compute correctness, where we only consider the triples that are most similar to the user query. So in that case, we would only consider the triples that are related to anxiety. But so this is just an idea, and I'm happy to take any question. Also, if you want to contact me, here is my email. So thank you, and that's it.
Thank you, Giancarlo, for your presentation. Now we have a 10 minutes question session. So I ask Giancarlo to remain online, and I ask the other two speakers to come here. Thank you. Okay. Any question for our speakers? No? Okay, I have a question for Giancarlo. And my question, I don't know a lot about this topic, so I don't know if it is a very simple question. But in your system, how do you manage hallucination? So in your system, when there is an hallucination, how can you think to solve it? Giancarlo, do you hear us? You are on mute. We are not able to hear you. Maybe he's hallucination.
The moment we are trying to solve.
Okay, thank you. Yes, there is some question from the audience. Okay.
I think it's a question for any of the speakers for this session. I saw that some of the models used in your work are better when combined. For example, I believe one was BERT with context, and maybe I missed it, but context was
a rule-based approach.
A rule-based approach, okay. I saw also, specifically for my work, because I'm planning for future analysis, the combination of a graph, a relational taxonomic knowledge to a vectorial embedding as also a better system, like an hybrid system that perform better. My question was just if you have any suggestion on how and why it might be better to combine systems, or it's just experimentation. Just
to start from the last one, definitely you need to evaluate it in multiple dimensions, in the sense that you need to see if they combine work well, but also consider all the cost, the efficiency. For example, we had the opportunity to use a BERT model fine-tuned to identify negation, but this is just an overkill because the context algorithm, and specifically the negex part of it, which was rule-based, was performing better. In the original publication, which is the first one I presented, we did many more combinations. We actually did all combinations of all the state-of-the-art models to perform this information extraction by that time. So, yeah, this is the second part. Did you answer your question again?
Are there any other questions from the audience? Okay. I don't know if we are able now to hear Giancarlo.
I should be unmuted. Can you hear me?
Okay. No. Yes.
Okay.
We can hear you.
Okay, so I briefly talked about how we can, maybe I can share very quickly my presentation again, but how we handle hallucinations, at least with respect to the extraction of triples from the BPD abstracts when we expand our knowledge graph, because for sure we want to reduce as much as possible the possibility of generating hallucinations and introducing hallucination in our knowledge graph, because we want to keep it as consistent and clean as possible. But still, LLMs could generate hallucinations when we use them to expand our knowledge graph. And so we tried to implement these safeguards to try to mitigate this possibility. Like, for instance, we saw that LLMs sometimes generated contradictory triples, but we got rid of those. And also maybe when LLMs used some words or terms that we could not trace back to the BPD abstract, we also excluded these triples. And this is with respect to the expansion of the knowledge graph. And when instead we extract triples from documents, triples that we want to verify, there is still this possibility of generating hallucinations, and we can implement similar safeguards, like checking that the triples that the LLM generates actually the terms, the terminology matches the one from the documents. But for sure, we cannot be 100% sure of not introducing hallucination, but we try to mitigate this possibility as much as possible. But also, we already also discussed this internally for also possible improvements of the system, and we were considering other tools to perform this extraction besides LLMs, also because LLMs come with a huge computational cost, and there may be other tools that are maybe less expensive and still accurate for simply extracting relations from text.
Thank you.
Thank you.
I don't know if there are some questions. Any question?
I have a question for you, Georgios.
Sí, sí.
Okay. And you showed us that the experts are better than the model. And my question is, could we imagine to transfer the knowledge of the expert into the model somehow? Not now, in the future. What is the perspective with respect to this point?
When it comes to medical applications, I personally believe that we cannot replace the human supervision, at least in the next, 5 to 10 years. I don't think so. And it's something that we shouldn't do. Definitely, we can improve the time and the cost. So we can have similar results, but instead of doing all the manual effort, the experts, we just let them with the supervision part. But I believe that that will be the improvements we can have for safety mostly.
Yes, but some of the experts were bad with respect to the models. So, okay, sometimes maybe it's better the model instead of the expert.
That's,
But you showed us different performances. And also I was curious about the meaning of that, the measure, the score that you used, because you said that it was the number of, among 10, out of the number of correct ones?
yes, on average across all patients. I can give, so that's great. The fact that we can have good performance by the LLMs and bad performance by experts, it's great for management, I guess, if they want to measure how effective are the employees in a sense. No, it can be a measurement of maybe you should do better than that. But again, no replacement at any point. Then another thing that was presented here, of course, these benchmark collections, they have their own faults, is that, let's say, doing nothing, and an expert doing this job, on average, will find 2.6 eligible clinical trials with standard approaches, and then going to LLMs, this can be improved to 3 or 4 on average. The question that we should, and any organization should ask, is this improvement enough in order to do the investment of this model? So again, it falls into management, these things. So.
Thank you.
Thank you.
Are there any other questions? Okay, I have a question for Davide. And my question is about the Euclidean distances. Why have you decided to exclude these distances in favor of the DVT?
Yeah, that's the main difference regarding the time series. So our collaborator Patrizia Ribino found this distance that takes into account the different time series that can also have different speed, different rates. And so by computing the distance between these time series, she understood that it's more informative than using the typical Euclidean distance, which it's because usually sometimes time series that don't reflect maybe the Euclidean distance, so that was the improvement.
But have you tried to compare the results with the two different distances, or no, you selected?
No, because it's more meaningful, makes more sense to use distance based on time series, since we have 5 visits, than using the Euclidean distance that maybe is for static data sets.
Thank you.
You're welcome.
Any other question from the audience? No? So I think we can close the section. Now there is a half an hour break as a coffee break in the same place of this morning. I don't know if all of you know where there is. If you have any question, come here, that will give you more information. Thank you.
Okay, welcome back to the fourth and last session of today's workshop. It will be about new technologies for well-being and rehabilitation. And our first speaker is Gaia Locatelli. She's a research fellow at the School of Medicine and Surgery at our University of Milan Bicocca. And her contribution is entitled Machine Learning-Based Algorithms for Emotion Recognition. The floor is yours.
Thank you. Thank you very much. And good afternoon, everyone. Today I will present to you a project which is the result of a collaboration between the Università degli Studi Milano Bicocca and the Politecnico di Milano on AI accuracy in detecting emotion. So, but what's in fact an emotion? An emotion is an internal process triggered by a relevant stimuli, which also involve subjective experiences, physiological changes, and expressive behavior. Whenever we are talking about emotion, we have to deal with two relevant factors, emotion expression and emotion recognition. So, human facial muscle involved in emotion expression are universal, and this could explain why facial expression are similar among different cultures and people with different abilities. Emotion, it's not only expressed just through facial mimicry, but can be expressed also through multiple elements. For example, facial mimicry is often accompanied by hand and eye movement, body positioning in space, or posture. Emotion can manifest also through changes in physiological changes, such as changes in heartbeat, sweaty palms, as mine right now, dizziness, and other things. The emotion can be expressed verbally through semantic content, which is the word that we used, and prosody, which regards elements as intonation, tone, timbre, and speech. Numerous studies led to the development of a variety of tools aiming at facilitating emotion recognition. In this context, the application of AI in detecting emotion are increasing, and using different approaches from text analysis to multimodal approaches. So, considering all this, our aim was to explore how accurately 3 different machine models were able to identify emotion in a more ecological context. Our first aim was to detect how well each algorithm will be able to recognize 5 emotions and to compare the algorithm between them. And after that, we wanted to test if the integration of these 3 algorithms would have increased our emotion detection. We decided to use 3 different algorithms detecting 3 different modalities. For text analysis, we decided to use text to emotion. For vocal analysis, we decided to use emozionalmente, while for visual analysis, we decided to use OpenFace. Text to emotion is a Python library that links certain words to an emotional state. Starting from English test, it calculates a global likelihood and intensity of each emotion, providing percentage, and it's trained on 5 different emotions. Emozionalmente, instead, it's an Italian speech emotional database trained on amateur actors who were asked to read neutral sentences and to interpret different emotions. The audio were very brief, and this model allowed to extract brief piece of audio, and then it updates the emotional evaluation in an incremental way. And it contains emotion like anger, disgust, joy, etc., etc. OpenFace instead is a toolkit dedicated to facial behavior analysis, and is based on 68 facial landmarks, 18 action units, dedicated to the determination of head orientation in space, but also to determine the eye gaze, eye gaze estimation. And this model allowed to segment the video in a small chunk, and it calculates the mean intensity of each emotion within each chunk. And it recognizes 6 emotions based on facts. So we decided to use a platform called Claudia, in which participants could answer questionnaires and then to record themselves while they were recalling 5 emotional episodes plus 1 practice trial. The instruction of our task was based on a tool frequently used in psychotherapy, which is the ABC model. Participants in particular were asked to recall the activating event, which is A, the thought immediately following the event, which is B, and how they felt and how they react at that event, which is C. To help participants within the recall, we present on the screen a series of questions that remained until the end of the registration. Our experiment has been divided into sessions that took place in 2 different days. The second session, in fact, have been held from 1 up to 7 days after the first session. During the first session, participants were asked to recall 2 emotional episodes, while during the second session, participants were asked to recall 3 emotional episodes. The 5 emotions were randomly presented during the 2 sessions and were sadness, fear, anger, calm, and happiness. At the beginning, we have decided to use just one positive emotion, which was happiness, but then we decided also to add calm and relaxed. During the first session, participants were asked to answer to 5 questionnaires in order to assess the possible presence of depressive or anxiety symptoms, their ability to recognize emotion, and their ability to regulate their emotion, but also their emotional state at the beginning of the experiment. After that, they were asked, in fact, to recall, to register themselves while recalling an emotional episode for at least 3 minutes. They could decide whenever to start and whenever they wanted to interrupt the registration after the 3 minutes. They could also continue to talk. After this, we asked participants to complete these 2 visual analog scale. A visual analog scale is a bar that goes from 0 to 10, and a subject is asked to rate an element. In psychotherapy is very used. In this case, we wanted to check the concordance between what the participant actually felt during the task, and which was the requested emotion of the task. In fact, we wanted to check that what the participant felt was, in fact, what we asked to recall. So we asked participants to complete the first VAS, in which we asked them to indicate how positive was the emotion that they felt, how much they felt activated, and how much they felt in control during the recall. After that, we asked participants instead to rate from a scale from 0 to 10 how much they felt a certain emotion. You can see linked here. The last element was the washout video. In fact, we asked participants just to simply watch a video to help them to get detached from their previous recall. And during the second session, instead, we asked participants to complete just one questionnaire regards how their emotional state at the beginning of the experiment, and then to complete the remaining 3 emotional recall. We were able to recruit 53 participants, all Italian speakers, through social networks and Sona system. Each participant was able to register all 5 emotions, and we were able to collect 265 recordings. From each video, we extract the audio tracks and then the test transcription, and to reach a total amount of 795 elements between video frames, audio tracks, and test transcription. We decided to perform different analyses, starting from the manipulation check. We wanted to check the emotional state of the subject while they were, of the participant, while they were in fact recalling the emotional episode, analyzing the affective, so the first VAS, and the emotional, so the second VAS variables. Checking the VAS questionnaire, in fact. Then we decided to analyze the level of accuracy on 2 bases. We decided to analyze the level of accuracy of each AI in detecting the request emotion, and then the level of accuracy of each AI in detecting the perceived emotion. At last, we decided to combine all three algorithms to try to extract the accuracy of each requested emotion, in detecting each requested emotion. Regarding our first results, a participant rated as more positive emotion, and rated as more negative emotion, as you can see on your left. In the middle, you can see that participant felt more activated while recalling most of the emotion I presented here, with the exception of calm and relaxed. And on your right, I think, yeah. On your right, participants felt more in control while they were experiencing positive emotion rather than negative emotion. These results are perfectly in line with what we have found in the literature. Before analyzing our emotional variables, we decided to check the concordance between the perceived emotion and the requested emotion. And as you can see, Cohen-Scappa showed a good agreement between the perceived emotion and the requested emotion. So participants actually felt what we asked them to feel. And as you can see, when a participant was asked to recall an emotional episode, he felt that the most activated emotion was in fact the one that we asked them to recall. But we also have other emotions activated. For example, if you watch on your top left, during the happiness emotional recall, participant felt more activated for happiness, but calm and relaxed is activated too. Okay, regarding our the accuracy of our tool, here you can see 3 different colors for our 3 different tools that we used. The text tool in orange is text to emotion, the audio tool in green is emozionalmente, while the video tool in blue is open face. And as you can see, the overall accuracy per each tool is higher for the text tool, but our accuracies are lower than the one that we can actually find in literature. Passing on the histograms on your right, and we decided to analyze the accuracy of each tool for each requested emotion. And as you can see, the 3 different tools have higher accuracies for 3 different emotions. For example, audio and text tool have higher accuracy for fear and sadness, with an accuracy of 77%, if I am correct, and the video tool is more accurate in detecting the happiness, with an accuracy of 71%. As we can see, the text accuracy for anger and the audio accuracy for happiness is nearly 0. Another element is that, as you can see, we decided not to consider calm and relaxed in our analysis because some of the tools that we used are not tuned for, in fact, calm and relaxed. So we decided simply not to consider that emotion in our analysis. And the last thing is that anger is, in fact, the least recognized emotion by this tool. But if we look closely at the confusion matrix, you can see how, in fact, some emotions have been mistakenly classified as other emotions. For example, anger has been misclassified for sadness by the text tool, or the audio tool frequently misclassify both anger and happiness as a fear. This could explain why some emotions have a so low rate of accuracy. Within the diagonal, instead, you can see the correct prediction for each emotion. Okay, until now I have just to talk about the accuracy for the requested emotion, but we decided also to check the accuracy of each tool for the perceived emotion, and as you can see, the percentage are very close to the one we found for the requested emotion, showing that there is an adherence between these two variables to construct the perceived and the requested emotion. Okay, regarding our last topic, which is the multimodal analysis, we decided to combine all three algorithms and then to check the accuracy for each requested emotion. And as you can see, we have the highest percentage for fear, of almost 68%, and then sadness with 45%, and then happiness with 15%. Compared to the accuracy we have found for each tool, our accuracy with all three models combined together are lower. Okay, to conclude, we can resume that our methodological paradigm is valid, showing that there is an alignment between the perceived emotion and the requested emotion, providing a more ecological evaluation. Through the comparison with the literature, as you can see in this histogram, the accuracy of our AI are lower than the one we can find in literature, and this could be explained also by the fact that most of the AI used that we can find in literature are trained on a specific data set, most of them using actors performing emotion, interpreting emotion, while we decided to use our AI on a more ecological data set. Then to resume, different tools are more accurate for in detecting different emotion, but there is also a tool's tendency to misclassify certain emotion. For example, anger have been often mistaken for sadness. Of course, our research has some limitation. The first regards the emotion intensity. Some approaches allow to increase the emotion intensity, but still, by the fact that we wanted our participant to talk, we decided to ask them to recall an emotion. And when you, in fact, recall an emotion, the intensity is lower than the moment you actually are feeling that emotion. So this could be one limit of our research. Another limit could be the complexity of emotion. In fact, when you experience an emotion, often you don't experience one single emotion, but you can experience multiple emotions at the same time. Another important limitation is calmness missing from most of the algorithms that we used, and it might be interesting to use other kind of algorithms to try to check their validity in detecting calmness. The last point regards the text-to-emotion. It's more text-to-text transformation, but the point is that in order to complete our analysis, we needed to translate our text from Italian to English, and this could have had noise on our data. So it will be more useful maybe to use another tool to tune on Italian text to analyze our data. Looking at the future, what we would like to do with our research is to implement also human raters. As far as we know, the accuracy rates are lower than the ones presented in literature. But we don't know, in fact, if our accuracies are low in absolute or not. So we would like to ask also to human raters, and I leave this question open, and I will appreciate any kind of suggestion that you have, because we don't know how to do it. And so if you have any kind of suggestion, it will be very appreciated. Another point regards the use of, as I previously mentioned, other machine learning to classifying technique to test on our data. And we are considering the possible use of large language models for emotion classification. And to conclude, I would like just to thank you for your kind attention.
Thank you. I think maybe someone will try to answer to your question later when will be the question session. So the second speaker is Teresa Di Bella. She's a PhD student at the Department of Psychology at the University of Milano Bicocca. And their presentation is entitled From Concept to Prototype, Our Serious Game Design Journey.
Okay, so good afternoon, everyone. I am Teresa, and as she said, I'm a PhD candidate in psychology, linguistics, and cognitive neuroscience. I feel like my presentation will be a little bit different than the other ones, as it is less technical. This was my master's degree project that I did under the supervision of Professor Rossana Grosso. And it's a serious game I designed for pragmatic abilities in atypical development. So let's start by defining what a serious game is. What differentiates a serious game from a classical, typical game is that is the purpose, because a serious game is designed to achieve educational goals. Okay, or support behavioral changes, for example, and it can be applied in various fields such as health, advertising, social, psychology, politics, and so on. So it shares key elements with traditional games. We have competition, we have the rules, we have the challenges, the possible to choose something. But in our case, all these elements are designed with educational goals. Kind of serious game can be edu games. What differentiates entertainment and edutainment is the fact that in edutainment we aim at teaching while entertaining. So we do not focus on pure enjoyment and engagement, but we prioritize learning. In this way, edutainment, the word is a merge between education and entertainment, can use entertainment to expand learning opportunities in non-traditional ways, and it's focused on engaging while teaching. So games are no more only for entertainment, but their motivational characteristics can be exploited to produce effective learning because it's active, experiential, and this game-based approach can be very motivating and enjoyable. So I put on this slide an example of motivational design that I found on the internet that I liked a lot. It's a gamified learning tool for learning the periodic table, in which the elements of the periodic table are conceptualized at the characters of an RPG games, and in this way we can learn about them and their interactions. An edu game can be designed for very different types of support. We don't have only video games, but we can have also analog games, such as board games, or even more like virtual reality. In my case, I will talk about a video game. So how did the project start? I went to Professor Actis Grosso and I told her that I liked the language and I liked video games, and I would have liked to make a video game for assessing pragmatic language in children. So starting from the fact that population with atypical development can exhibit language difficulties, which is a fundamental skill for a proper socio-emotional development. It could be useful to create a tool which is accessible and enjoyable and motivating for children, that could be used during the assessment session, for example, by speech therapists. So, my game, Watchword, is a visual novel for the assessment of this skill, which was realized following a user-centered design and developed with RenPy, which is a Python-based engine. Regarding pragmatics, I don't know if every one of you knows what language area it is, but pragmatics studies language beyond the literal meaning of a phrase. So if we say the same phrase with a different tone, it could be interpreted as ironic or as rude and so on. I said that Watchword is a visual novel. What does that mean? A visual novel is a game genre. There exist many genres. I put two as an example on the slide. For example, puzzle game requires strategic thinking, and platform games require twitching skills. So depending on the genre, we will be requested to use different skills. In specific, a visual novel is a semi-interactive fiction that has a narrative that can be static or animated, and is quite interactive, as the player can choose to can make choice that influence how the story goes. They can create their character. It's much interactive. We choose this kind of game because it focuses on language and interaction a lot, but also because it's not difficult. So if I think about it in an assessment setting, neither the player or aka the child or the speech therapist has to learn complex gaming skills. And also, it has a very predictable gameplay with the static and easy predictable mechanics that can be ideal for atypical development players who might be disturbed by some of the typical game features. So in this way, we combined technology and assessment. This game is based on an already validated the assessment method for pragmatics, which is the short story method that I will explain shortly. And the focus on this game that combined together can become an engaging tool that serves both assessment and intervention goals. Here we go in the game. As I said, it's based on short stories. Short stories are a method based on the narration of stories that have different implications, such as irony, lies. Here I have irony and 3 types of lies, in which a story with one of these implications is narrated. I explain myself better. We see 2 characters that interact with each other, and at some point in the story, one of them says a lie or says something ironic, and the player has to understand what is happening, so the reality of the story, and what the characters think about what has been said. So we have questions in this method to understand if the children understand about reality and the speaker's belief. And the children has to answer with this answer interface composed by 4 possible answers, which are 1 target, 1 competitor, and 2 distractors. For example, we have a story about a child who lies about their room being tied up. And in this case, if I ask the child, how is the room right now, the target answer, so the correct one will be the down left one, while the competitor will be the upper right one, the tidy room. Now I will present the structure of the game. So in the game we have different characters. The child or the player has their personal avatar that can be customized and named. We have a game mascot that is the narrator of the game, and each of the short stories has 2 protagonists that have names, their scenarios, their personalities, and so on. As I said, the player can play the short stories we thought of, which are 4 in this base version of the game. Each of the story has a mini game that does not serve assessment purposes. It's not related to language, but it's present to foster active engagement, and we also have optional quests to enrich the gameplay further. We tested this very base version of the game, I will call it the alpha phase, with game testers. I presented it to 16 last year game design students in University of Barcelona, and I asked them to provide feedback on game design, graphics, storytelling, programming, everything that needed attention in good and bad ways. So in this stage, the game had 4 stories, and it was not dubbed. And I asked the students to give me feedback on game design, the narrative quality, the graphics, the bugs, after presenting them a presentation about the objectives, the goals of this game, to make them understand the psychological and linguistic background of the game. So this phase was important to introduce them to the actual rationale behind the game and make sure they gave us focused feedback to avoid unimplementable suggestions. So after the presentation, they played the game on their workstation and took notes on everything they noticed. And after the gameplay, they completed a feedback questionnaires regarding their demographics, questions about their game experience, and a free feedback space where they could give me a general evaluation of the game. Of course, everything was anonymous. And this phase was very useful because we collected feedback on several aspects of the game that helped me understand what was working and what was not working about the game. So this highlights the importance of involving also user in the testing phase in order to making sure that the game meets its objectives. Here I have a list of things that I changed after this first testing phase. So we changed the game buttons, which were not visible. We changed the text clarity because we had a wall of text that could be overwhelming. We gave feedback on questions and changed a little bit the answer interface. Changed the font. They all regarded the usability of this game, and I also solved some bugs. So after this first redesign, the game was dubbed, so each character received a voice. They were dubbed by amateur actors, which paid really close attention to prosody, which was crucial because we have, as we said, this game is on pragmatics. So, for example, in irony, the tone of the phrase is crucial in understanding, as we will see later. And after this first redesign, we proceeded to do a second testing. So we tested the game on adults. They were 40 adults. We didn't test on children first because we needed to make sure to understand that the sentences, the stories were understandable for adults, which should have reached at least a great pragmatic competence, so it was crucial to test with them. They were divided in 2 groups of 20. One played the version of the game with dubbing, and one played the version of the game with no dubbing. So we had 10 of them per group play the ironic story first. because during the testing, I had the impression that the ones who started from ironic story could understand irony, and the one who started from any of the other stories couldn't understand irony. So to control this condition, I made them begin from the ironic story. Later, then after the game test, they completed the same questionnaire that Game Design Studio completed with free feedback and item on how they liked which aspects of the game they liked, if they find it boring, and so on. And here I have the results of this test. Please notice that the graph that I present here is only about the understanding of irony in the speaker's belief question. That's why everyone understood the reality questions, so everyone knew what was happening. Not everyone understood what the characters were thinking. This was particularly true for irony. In fact, you can notice a really, really, really low score in irony for the condition with no dubbing, underlining a role of prosody, and a little bit high understanding in participants starting with ironic stories, but still unacceptable because only 30% of them understood the ironic story. In the dubbed condition, this changed a lot because we have an overall understanding of 63% in irony. But if we consider only those participants who started with irony, 9 out of 10 understood it, underlining a role of prosody and a role of the order of the presentation of the story. So this has to be kept in mind because it can affect an assessment stage in a great way, in a huge way. These are the results about the liking of the game. It received an overall good evaluation because the participant thought that the game was fun, it wasn't boring, it was aesthetically pleasing, and most importantly, it was easy to progress in the game, so it wasn't a difficult tool to approach to. Now, after collecting this feedback and after this test, we are working on adding more stories to our game and editing the stories that were unclear as emerged in the tests. But most importantly, we gained feedback from speech therapists that work with target population. We are working with La Sacra Famiglia, and they worked with children with autism. It was very useful to show the game to them and collect their feedback because they gave us very valuable insight. For example, they told us how to better write our sentences. They told us, for example, to give a lot more information and repeat a lot of information in order to make the context clear in the stories. They also gave us their feedback on the mini games, which could be maybe really difficult for really young children or with children with a very low functioning, for example, in autism. So we are now implementing these suggested changes, and we hope we can test with children as soon as possible. Thank you.
Thank you. That was different, but indeed interesting. So the next one actually will be the last one for today. Eleonora Kitty, you can come. She's a postdoc research fellow at the Department of Computer Science at the University of Milan. And her presentation is entitled Mixed Reality Applications to Support Freezing of Gait Rehabilitation.
Hello, I'm Eleonora Chitti, postdoctoral researcher at ISLab, Applied Intelligent System Laboratories at University of Milan. And currently I'm working on the ARCA action interaction between humanoid robots and children with autism, with Prof. Rossana Actis-Grosso also collaborating to this project. So many friendly faces today. And but today I will talk about a newborn project about the freezing of gait rehabilitation for patients with Parkinson's disease. Let's start from the beginning. What is freezing of gait? It is a symptom in Parkinson's disease that increases the risk of falling and occurs when a person has to pass through a doorway or narrow spaces, and the person freezes and has difficulty to resume walking, even shaking in that moment. And conventional physiotherapy is useful to train gait in these patients, and in particular cue-based exercises, so exercises that implement some, let's say, aids or help that allow the patient to resume the walking. For example, visual cues that can be floor stripes on the floor, or auditory cues like music or metronome that gives the cadence rhythm of walking. However, the currently limitation of conventional physiotherapy is the manual setup of the training. So before starting training, the clinician has to attach the stripes on the floor. And this can solved with brand new digital tools for gait training. And different applications have been explored in literature to perform gait training, like non-immersive representations of virtual environment in which the patient moves by walking on a controller that has foot pedals. So the patient really walks, but in a virtual environment. And more recently, an augmented reality application was proposed using Google Glasses that implements visual aids. So the patient's walks are already watching digital visual aids on the floor. But only with the rising of mixed reality, so with digital elements integrating physically in the real world, digital gait training boosted. In fact, mixed reality is safer and less disorienting than a full virtual reality in which you cannot see the real world, but integrates digital elements physically in the real world. And thanks to new technologies as Oculus Quest 3, now it is possible. How this project started? This project started thanks to a student, Pierpaolo Serrano, a master student, that arrived to our laboratory and said, okay, I have an Oculus Quest 2. I know that pass-through is in black and white and is only for safety purposes, but I want to do a game with that. We were starting to have some contacts with Professoressa Ferrucci from University of Milan, Department of Oncology, and she is also working at the Department of Neuropsychology of Polyclinic, and said, okay, let's merge the two things and do something for Parkinson using Oculus Quest 2. And we started a prototype and exploration, implementing two versions of virtual reality and mixed reality of the same application. There are crowds of people, virtual people in the real world or in the virtual world, and the patient has to walk within them. So we represent narrow spaces using virtual people. this was an exploratory study, so we involved 10 people not suffering from Parkinson's disease for the first study to access the perception, here there is a mistake, is mixed reality, MR and VR experiences, and to collect their feedback on which of them they preferred, which of the two experiences they preferred. And so each participant wore the Oculus Quest 2 at the time and tested both the experiences in sequence. First one, and then he activated the other version. And they scored a questionnaire of ease of use, immersiveness of the experience, discomfort related to the wearing the headset, eyes discomfort, and nausea. And they reported that widely preferred the mixed reality experience. None of them reported motion sickness. They well felt more safety since they could watch the real world. And only 2 users, 2 and 8, reported uncomfort in both the experiences, but they were wearing glasses. At the time of Oculus Quest 2, we didn't have the distantiator for glasses, so it was still uncomfortable for eyeglasses users like me. And user 10 refused to wear the headset, so was excluded from the studies. Was a young guy of 20 years old. With this prototype in hand, we started a co-design process with the team of Professor Roberta Ferrucci from the IRCS Carranda Ospedale Maggiore Policlinico, and on the computer science part, me, the MSc student Andrea Montereale, and Professor Alberto Borghese. So we started a co-design. But I will start from the end, so I will show the final application before describing the whole co-design process. How XR, the brand new version of XR Fog framework is composed. We have 2 components, the headset application for Oculus Quest 3. Now we have the colored pass-through, and we implement a real mixed reality, not a fake dark mixed reality for Oculus Quest 2, and a companion application for the clinician that can control and customize the exercises in real time, even activating and deactivating cues at runtime. And we decided to leave apart in this time the crowded exercise because it was too complicated for starting gait training. And we opted for 2 traditional exercises for this version of the framework. That is the obstacle course, so virtual obstacles appear in the real world. They can position in any point, so making different kind of courses. And a corridor with arcs or doors. So we have a straight corridor that can be adapted in width and height with an arc at the end that the patients have to pass. In the other version, the arc is closed, so there is a door, and the patient has to stop before the virtual door, turn around, and go back. The cue types implemented are stripes, traditional stripes on the floor, footprints that the patient can follow stepping on them, and a red dot that traditional therapy implements with a laser light. So clinician usually helps the patient to resume walking, pointing a laser light in front of the feet. We implemented that virtually, making a red dot appear in front of the feet of the patient. And about audio cue, metronome and music that can be adapted in the BPM to respect the cadence, the walking cadence of the patient. How do we arrive to this framework? We started demoing the original Oculus 2 version of prototype to the medical team, and obviously mixed reality was preferred over the virtual reality version. And we selected the 2 key exercises, and also from the beginning it was required a real-time customization. So they opted for 3 types of obstacles: cones, bin, and core tracks, that are different in height, so they increase the difficulty. A core track is more difficult to pass by with respect to a cone. And also the obstacle can be substituted at runtime in the path. And the corridor walking that I already described, that can be customized in width and height. Also, the final arc can be customized in width, height, and can be closed. The first 2 visual cues that we decided to implement in this workshop were the stripes and metronome and music pieces. The first version after this workshop was implemented only for Oculus Quest 3, so customization was done in real time using the controllers of Oculus Quest 3. But in the second workshop, when we presented the application, we observed with the medical team that it was not feasible because it was the patient that was wearing the headset. So it was not possible to adapt in runtime the exercise or to activate the cue, since it was the patient that was walking with the headset on it. So we opted to remotely customize the exercise implementing a companion app. In the same time, we also observed the need of the clinician to observe the point of view of the patients. So in this framework, we decided to give two tablets, one with the companion application and one with the Oculus official Meta application, allowing to view the same view of the patient. But it can be implemented also on the same PC with a double window, one of the companion on the side and the Oculus link on the other side, link application on the other side for mirroring. And we also added more visual cues, the laser dot and the footprints. Once we arrived with the companion app, the Oculus Link application, and the headset application, we tested it with 2 patients with Parkinson's disease. One of them was suffering of freezing of gait. And they tested, each one of the participants tested both the obstacle and the corridor task. While testing the obstacle, they tried in sequence a path with cones, a path with beams, and a path with the quadrats. And then they tested the corridor. During the obstacle track, all the cues were shown, and there were the clinician present. So if the fog occurred, the clinician chose the kind of cue to activate, also based on the feedback given by the patient. And for the patient suffering of fog, the clinician asked to adapt the exercise in real time, so moved the cones near a rear wall and asked the patient to move in this strict passage to, in some way, induce fog and watch what could happen. Obviously, there were 9 clinicians and 3 computer scientists in the moment. So we effectively saw that freezing of gait was triggered, and in this case, the stripes on the floor and the music combined together, helped the patient to resume walking and start again to walk. Final refinement of the platform was to add a step length customization to visual cues. In fact, we added the possibility to customize the distance of the 2 feet in the visual cues, and added also more music. In fact, the patient said, okay, the march is boring, I want more pop and contemporary music. So we added a wider set of music to that. And also both the patients reporting very no motion sickness, and also they felt comfortable in using it for the time, in using the application for the time. So what we developed, this is the whole framework, an Oculus, a tablet with the mirroring application from Oculus, the XR companion application working in the same local network, and the MetaQuest 3 with the headset. Yes, these are the screenshots with the stripes and the feet on the floor. We are currently doing a usability evaluation. That's why it is preliminary, because the study is still ongoing. And we are recruiting patients with Parkinson's disease. For now, we tested with 14 users, but of them, 10 have Parkinson's disease. And we performed, they did the same exercises we performed in the workshop 3, so obstacle course with the 3 kind of obstacles, then all the cues, then the corridor. And the score, they then filled the system usability score, and the scores were interesting. So we had 80, a mean of 80 SUS score for users with Parkinson's disease. And none of them reported motion sickness. They said, okay, it is interesting, perceived as safe. A patient said that she already tested other kind of applications of virtual reality, and she was feeling uncomfortable. But in this case, since she could see the real world, she was feeling safe, different feeling from full virtual reality. However, we, thankfully to Oculus Quest 3 that has the distanciator, we had to calibrate the headset for glasses wearers, but also this improved with respect to the Oculus 2 first test. So, in conclusion, mixed reality shows great potential for freezing of gait rehabilitation, more than virtual and augmented reality. And so the co-design with the clinical teams allowed us to answer to their needs, hopefully also improving it with new exercises, even more difficult for training gait. And the preliminary studies shows usability, but we have a small sample study, small sample size, the study is ongoing, and we also should perform a longer study. Now it is one-shot test and score. We need to perform a longer evaluation. And also, eventually in the future, our hope is to integrate also a set of logs in the companion application, logging the gait of the patient during the training, the walking cadence, and logging different useful information for the for tracking progresses of each patient. So this is the project, and thank you so much.
Yeah, you can stay here, and yeah, the other 2 presenters can come. So, if there are any questions, you're free to ask.
Questo, sì.
I have some question for you. Yeah. I saw from your group of participants that it was quite unbalanced toward female. You have a lot of female. And also, I'm from vision, then I'm not, I don't know anything about the voice, the text.
Okay.
I'm only talking about the visual aspect, which is my field of expertise, actually emotion recognition then. And also, I was wondering, given that they were free to express their emotion as they wanted, if you evaluated the difference when showing happiness, showing your teeth or not. Because it's something that someone is smiling. For example, when I smile, I don't show my teeth. Instead, there are many people that smile like that. That is quite important for visual facts. I mean, this is the question.
Okay, so regarding this balance between female and male, it's an ongoing problem within the psychology because most of the time. But it's in fact it's a good point to point it out because. I mean, we didn't consider it as a big problem, but it should be better, of course, to balance between the two gender. Regarding your
I understand that maybe it's difficult to collect mail. Just make an analysis in which you evaluate whether there are some differences.
No, we didn't do it. Also because of this disbalance, we didn't check between.
Because if there is no difference, you do not have to balance.
Mm-hmm.
Just check it, okay?
Mm-hmm. Okay. Regarding the fact that you were pointing out about the difference, which is in fact from subject to subject difference on how you express emotion, we used pre-trained algorithms that detect different. They detect certain part of the face that can be related with a certain kind of accuracy on and be related on a certain emotion. Of course, as you have seen, this kind of project is not. It can be also. How do I say, subject to some limitation, not just as we were saying by the fact that there are some subjective difference on how a subject expressed their emotion. For example, we have also cultural difference on maybe another person that from a different culture express emotion differently from us. But the point is also on that we have a 3 minutes recording, and so in 3 minutes so many emotions can pass by. And also
Okay. I can see them as a limitation. I mean, it's life. You did an ecological study, then in life everybody is showing emotion in a different way. And people, when have to decide what emotion you feel, they are quite accurate. Then I don't see them. On the contrary, I think is a strength of your study. Just to check for the difference, not try to make people all the same.
Okay.
This is my point.
Was your suggestion to check between? Okay. Well.
Just to check, maybe increase the number of participants so you have a large amount, and then check whether there is some difference. Because also working only with human, different type of population, I work with a lot of neurodiverse people, we can see that, for example, some emotion are more expressed by the face, some other by the body, only with vision. I cannot imagine if you are working with voice and prosody and semantic, then is check for different, you can cluster, for example, different emotions and, of course, different AI.
Okay, we'll try to do that. Thank you for your suggestions.
I think, okay. There was Professor Gasparini and also, okay.
A question for the serious game presentation and maybe also the mixed reality one. You talked about briefly engagement. You put mini games to improve engagement. It's just an interesting topic. Do you think there's let's say, might be a role in increasing engagement to very high level, even, let's say, addictive kind of level? Because video games nowadays, they can use a lot of strategies to make people, let's say, dependent on them. And so it is possible to increase engagement to such a level. Is it conflicting, you think, towards a therapeutic objective, or maybe it's a good addictiveness?
Yeah, okay, of course that's a risk. In my case specifically, my game is made for being used during the therapy session. So the game used by the a child with atypical development will be played by her or him with the therapist only in the therapy session. So it's not something that he can access freely, but it's inserted in a structured environment.
Okay, it is not the case of XRFog because XRFog is mainly for training, but this is the long discussed theory of flow that we usually implement also in serious games. So keeping balanced sorry, I move. Okay. Keeping balanced the ability, the performance of the player, the ability to play, avoiding frustration. So the engagement is difficult to achieve, but it is an equilibrium balancing the two tasks. So depending also on the target you are for which you are developing the game, you should use a kind of difficulty and also kind of different rewards. Children are very different from elderly people, but what we use is the bidimensional theory of flow. So we try to keep it balanced. Yeah, we have not frustrating, not so too difficult for the target users, but engaging. So you should give the rewards to them. You should allow them to win. While I was I'm talking about a very old project with children with epidermolysis bullosa. They can do very little movements with the arm, and in that case, the games should be very, very easy, implementing two kind of moves, allowing them to having rewards while doing the correct movements. This is very different for other kind of targets. But the principle is the same for engaging traditional gaming. But traditional gaming, you should kill the enemy with a lot of tricks that you do not implement in serious game traditionally.
Thank you. Do you have a question? Okay. Claudia? Thank you.
Thank you. I have several questions actually regarding emotion recognition, but I will start from the end. You said that you put together all the models and you obtain a multimodal approach. I didn't understand how did you put them together, because you have 3 responses. What was the way you combine them?
So, allora, we try to combine the outputs by simply merge them by summing up, and then to extracting the column that represent each requested emotion with the highest the highest percentage. So those are preliminary results, and I don't know if they are this is in fact the most correct way to extract it. So if you have any kind of any suggestion for us, it will be very, very helpful. I try to do it just to see if there were some changes in our results, but maybe it's not the correct way, or it's not. But surely it's not a better way. So any kind of suggestion.
We can discuss about it. And one comment: I'm not surprised that the results that you obtain were lower with respect to the result in the state of the art. The main reason is that they train and test their algorithms on the same data set. Sometimes they do that in a proper way, but in any case, the data were acquired in the same environment, in the same way, and you acquired the data in a different way. So I think this is perfect aligned with what we usually obtain. I was also curious about, you said that you recorded 3 minutes of speech, and did you divide these 3 minutes signal into window and process each segment, or did you apply the algorithms on the whole 3 minutes length recording?
Okay, so regarding the algorithm application, I'm not the best person to ask it to, but no, I think they apply the algorithms on all the registration, I think. From the regi, they tell me yes.
We will talk about it maybe deeper in the future, because this is related to the fact, the same point previously underlined, because, and again, you also commented that within 3 minutes the emotion is going to change. So it's interesting to divide the interval of time in segments and analyzing them. But we will maybe continue this discussion in the future. Thank
you very much.
I have also a question regarding to the last contribution. I was wondering if the patients can use this tool by alone, or they always require the assistance of a caregiver or someone else.
This is a very important question, because as it is now, the presence of the caregiver is fundamental, because it is the caregiver that changes the setup of the exercises, also activates and deactivates the cues. We kept also the possibility to trigger them with the controllers, but for now, none of the users they dropped the controller on a table and moved without it. But we received open feedback asking to have more control on the platform. Maybe we implementing hand tracking in some ways, but it is a feedback we received a lot from patients. So they would like to bring to use it independently. Absolutely.
Thank you.
Are there any other questions from you?
I have a curiosity about the game, the second speaker. The game is for a single player now, right? And do you think it's possible to extend it to a multiplayer where the child can cooperate between them to achieve the solution of the game? Or you think it's difficult?
I mean, it would be possible, but it wouldn't make sense. Since the game takes the short story methods already validated and makes it a game. So we follow a specific method. It's not anything we invented from scratch. So something like you suggest would be a whole another method of, I don't know, investigating children pragmatics ability, maybe useful to practice, but it would be a different thing.
So I also had two questions, one for Teresa about her serious game. You've mentioned the role of the motivation augmentation in the edutainment. And I was curious about if you implemented like a measure of this motivation augmentation, or you've compared the results from the validated short story system or the gaming system.
No, we didn't, but I think we should in the future. Like, we have only measures that tell us how the player, how much the player enjoyed the game, but we didn't measure motivation in specific. I think that's a great suggestion, so let's keep it.
Yeah. Thank you. So the other question was for Eleonora. You've mentioned multimodal cues, and I'm very curious because I also I'm interested into audiovisual stimuli, and I was curious about did you compare the effects of the only the audio stimuli, only the visual stimuli, and the effect of them together? Because I was like, yeah, it's a great result, but maybe just one of type could be enough, or maybe, as in other fields, the audiovisual is always better. So I was curious also about this field.
Yeah, this is a really preliminary study. Say that, yes, we already implemented the possibility to activate one or both the stimuli. So you can decide to activate only the audio, only the visual. And the red dot is independent from the other two kind of stripes or feet that are obviously mutual and audio cue. And this is a really interesting future exploration to do, because for now we wanted to assess the usability of the platform. So we activated one cue each time. During the third workshop, first we have shown one cue, then the second, then the other, in sequence, let's say. But when the patient experienced fog, we activated what he asked. So it was a one-time occurrence that was treated by the expert in that moment. No, it is not a long study result. But this is a really interesting suggestion for a long time. Future studies, we are still doing that, so we can collect also this data. So absolutely, it is a suggestion.
Thank you.
Thank you.
Okay, are there any other questions from the public? If not, we can close this session. So thank you all, and thanks you also for being still here until the very end. So if you want to stay, we can proceed with the round table.
Before the round table, actually, I want to really thank all the group, my research group, because they did a very nice job in organizing this meeting. And in particular, I want to thank Aurora Saibene, which was not able to come today. She is at home. She follows us. She followed, and she's still following us behind the scene, but she did a very great job. So I really want to thank her in particular and the rest of the team. And we can thank all of us.
Can someone take a photo of us, please? Daniele or Simona, can someone take a photo of us?
We want a photo. All of us. Okay, thank you. Okay. Then we need the Photoshop processing before making them available.
That's why I'm in this research group.
Okay. So for the roundtable, actually, I will leave you free to comment and suggest maybe what we can do in the future, because I think these activities, this activity and similar activities are really interesting, because put together different competencies, different backgrounds, disciplines, and so it can increase our knowledge and also produce great results for future work and collaboration. I found a lot of interesting stimuli. So if you have suggestions, what we would like to do is, of course, to repeat again the third edition of our workshop next year. Not on Friday, to avoid strikes problem. This is for sure our suggestion. One thing that I was thinking is to try to organize like webinar during the year with the relevant topic. So if you also would like to suggest a topic, or if you know someone that can can be the speaker, the person that can produce this in this talk, I really would like to have your suggestion, because if we can continue to stimulate our group, I think it's a great occasion also. Not only this event, which is going to be only once a year, but maybe we can try to define other activities that will enforce our collaboration and this group. This is my point of view, which is not maybe the round table that you were you had in mind, but
Yes, so we are very happy to get any feedback. If anybody of you wants to give suggestion or advice for the next edition, don't be shy. Otherwise, I'm gonna start to call by names. First, Marco Cremaschi. Dai il microfono, dai. We want to have your feedback.
No, non parteciperò più. Everything's very good, good organization, super interesting presentation, and
Especially mine.
smettiamolo. Comunque, niente, anche il coffee break, buono.
Okay, Anna Maria, do you want to say something? Microfono.
First of all, thank you for involving me and my group. Unfortunately, my collaborators are not here now, but I think that this kind of days workshops are very useful because they are the opportunity to speak each other, to present our works, to identify possible collaborations, and to know which other people is doing on similar subjects, and to have new ideas for, let's say, new projects and something like that. So very, very useful, and I hope a next edition will be organized next year. Thank you again.
Thank you, Anna Maria. Very nice words. Other comments? I'm gonna call Rossana. I'm sure you wanna say something.
Was already going.
No, I have nothing to say. I have nothing to say. I agree with Anna Maria, of course. Maybe if I can say something is that this sort of workshop, from my point of view, are also very important for the young people. Because, of course, we can network one each other by email. Maybe it is true, you always discover that someone else is doing something. But for young people to motivate them, engage, like in a video game, could be important. Especially small groups, easier to networking than... I do not have any particular suggestion. I think it's good as it is. I don't want, do you remember we already touched this point last year? I really don't want it to become bigger. Mm-hmm. Let's stay a very exclusive group of people.
Exclusive, wow. I just want to add, actually not add, I just want to thank my students because I saw them here. Yes, I was really happy to see that they catch the opportunity to come and to maybe learn something new, or also to know what we do inside of the university besides the teaching part. So thank you very much, because I was really happy to see you here. And this is, I think, a nice thing. Also, all the young researchers, and today was the day of the young researchers because we decided to give a special attention to their work. And also this is very interesting because talking about emotion, I felt during the presentation the motivation, the passion with all the person here. So I think it's a very nice thing to see.
Yeah, it's also good training.
Exactly.
It's also good training for young people for this, before going maybe to a big conference to talk in front of colleagues. Yes.
Yes, it's a very, also for us, to be chair.
So any feedback from that side, the other side? The
other side.
The third side of the...
Non funzionerà. Ah no, funziona. Okay, so it's difficult to speak at the last one because everything has been said. I think maybe one point can be next year to present also research project, not only done studies, because I noticed that every time study already run. So it's like I have an idea of doing this. What do you think? Because I noticed that we are sharing methodologies because we are strong, more or less, on the experimental, psychological, or physiological side. You're stronger in the technical and informatics side. So it can be interesting, I think. Even I don't know the format, it can be like a session in which instead of presenting studies with results, the young people that I agree they should be engaged and involved can present research ideas. So I would like to explore this. What are your suggestions? So leaving more space to debate and discussion rather than on presentation. That's my hint.
I think it's very nice, a very nice suggestion.
Yeah,
yes.
For the future projects, yes.
Yeah.
Okay. Then I think it's time for spritz.
No, one last comment I would like from our new colleague Simona Menta. She really wanted to say something. I read her in her eyes, so please.
Yeah. So I'm the last one, Leo, not you. No, actually, it was really interesting for me. So yes, I'm new colleagues in informatics, some older colleagues for a psychologist here, and it was, I think, very interesting to see a connection between the two words with these highly technological, really applied aims. It was really, really interesting for me. And then personally, I appreciate a lot of the studies also involving large language models, which are very popular at the moment. I appreciated the very grounded way in which all LLM studies were presented, highlighting also the issues and what we don't know about LLMs, which is something that on the psychological side, to me, it's very relevant because we've been using them. Well, it's easy to use them, very easy to do, but it's a blackish box that we are still trying to explore and figure out. And I think this is also critical reflection that should be at the forefront, because just using tools without understanding what they're doing could be very dangerous, especially, as some of you said, when we are dealing with medical sciences, physiological science, where the issues could be very dangerous in a way, it's impactful. So that was really interesting for me to see. Yeah, so thank you for organizing this wonderful workshop.
Thank you for your feedback, Simona. Any other comments? No?
Yes, spritz, as Eleonora said.
Chiudiamo.
Okay, I think we can maybe conclude our day, because it was a long day. We started early this morning, so we can leave you free to take the last underground. But also, I hope to see you next year, and we will send you news about what we are going to do, because we have all your emails, so don't worry, we will reach you. And thank you again for being here, attending this workshop.
And thank you, Francesca Gasparini, our leader, that organized it all.
Thank you all. Okay.
One last things. We are going to give to all of you the presentation of today. If some of the speaker doesn't want to share his presentation for any reason, please write us that we don't share it. So if you we are going to share by the next week. So if you don't want to share the presentation, please ask us or tell us in person, as you prefer.
Thank you all.